Dear students, in this video we are going to study about electrostatic shielding, electrostatic induction, dielectrics or insulators, what are polar and non-polar molecules, then induced electric field inside the dielectric, and then about dielectric strength. We know that the conductor has no parallel electric component on the surface, which means that charges can be moved on the surface without doing any work. This is possible only if the electrostatic potential is constant at all points on the surface and there is no potential difference between any 2 points on the surface. Since the electric field is zero inside the conductor, the potential is the same as the surface of the conductor. Thus, at electrostatic equilibrium, the conductor is always at equipotential. Now let us study about electrostatic shielding. Using Gauss' law, we can prove that the electric field inside the charged spherical shell is zero. Further, we can show that the electric field inside both hollow and charged conductors is also zero. It is very interesting property which has an important consequence. For this, let us consider a cavity inside the conductor as shown in the figure 1.46a here. And whatever be the charges at the surfaces and whatever be the electrical disturbances outside, the electric field inside the cavity is zero. A sensitive electrical instrument which is to be protected from external electrical disturbance can be kept inside this cavity, and this is called electrostatic shielding. So you can write this answer for what is electrostatic shielding. So here is the diagram for electrostatic shielding, and this is called as Faraday's cage. Now let us see what is a Faraday cage. A Faraday cage is an instrument which is used to demonstrate the effect of electrostatic shielding, and it is made up of metal bars as shown in this diagram. If an artificial lightning jolt is created outside, the person inside is not affected. During lightning accompanied by a thunderstorm, it is always safer to sit inside the bus than in open ground or under a tree. The metal body of the bus provides electrostatic shielding since the electric field inside is zero. During lightning, the charges flow through the body of the conductor to the ground with no effect on the person inside that bus. Now, next we will study about what is electrostatic induction. We have already learned that an object can be charged by rubbing using an appropriate material. Whenever a charged rod is touched by another conductor, charges start to flow from charged rod to the conductor. Is it possible to charge a conductor without any contact? Yes, we can charge it. And that type of charging without actual contact is called electrostatic induction. Now, let us consider an uncharged conducting sphere at rest on an insulating stand. Suppose a negatively charged rod is brought near the conductor without touching it, as shown in figure 1.47a, like this. The negative charge of the rod repels the electrons in the conductor to the opposite side. As a result, positive charges are induced near the region of the charged rod, while negative charges on the farther side. Before introducing the charged rod, the free electrons were distributed uniformly on the surface of the conductor, and the net charge is zero. But once the charged rod is brought near the conductor, the distribution is no longer uniform, with more electrons located on the farther side of the rod, and positive charges are located closer to the rod. But the total charge is zero. In the second case, now the conducting sphere is connected to the ground through a conducting wire, and that is called as grounding. Since the ground can always receive any amount of electrons, grounding removes the electron from the conducting sphere. And it should be noted that positive charges will not flow to the ground because they are attracted by the negative charges of the rod. And that is shown in this diagram B. So here is the thing, grounding. And since the ground can always receive any amount of electrons, grounding removes the electron from the conducting sphere. And we should note that the positive charges definitely will not flow to the ground, and they are attracted by the negative charges of the rod, as shown in that diagram B. Next, we will consider when the grounding wire is removed from the conductor, the positive charges remain near the charged rod. That's shown in figure 1.4c here. Now the charged rod is taken away from the conductor. As soon as the charged rod is removed, the positive charge gets distributed uniformly on the surface of the conductor, and that is given in D. By this process, the neutral conducting sphere becomes positively charged. So for an arbitrary shaped conductor, the intermediate steps and conclusion are the same except the final step. The distribution of positive charges is not uniform for arbitrarily shaped conductors. Why it is not uniform? That is discussed in the next section, 1.9.
We're going to charge these two spheres by induction. So the two spheres are the piece of metal. And we have them touching right now. And electrons can easily move from one to the other when they're touching. So it's essentially one piece of metal. But later when we move them, that's a way to cut them. We don't really have to cut them. We just have to separate them like that. But when they're touching, the conductance across that gap is pretty good. So we think of it as one piece of metal. I'm going to bring my Teflon rod, charge it with fur, bring it close, and it's going to create a separation of the two charges, or of the charge in the metal. So if I do this, here's a negative charge, I bring it right here. It's pushing negative charge over here, and it's leaving positive charge over there. Right? You didn't see anything. Well, there's nothing to see. Right? So let me charge it up again, bring it over here, and now I'm going to cut. I'm going to separate them. And now we just charge the two spheres by induction. And of course, you can't see it. I'm going to try to prove it to you with a little bit of Teflon tape. Right? So we know if we rub fur on this Teflon tape, we know it ends up negative. So if this thing ends up negative, then they should repel each other, or the tape should be repelled. And sure enough, you can see the tape is repelled. Doesn't want to touch the metal. And we should have left the other one positive. Oh, and sure enough, it's positive. It's very sticky for the tape. Okay? So we can use our Teflon rod, or our Teflon tape, to confirm it really did what it was supposed to do. Repulsion there. There's one other way we can confirm it, is when I bring them together, if you look very close, you can see a spark jump across the gap. The negative charge, the positive charge comes back together, makes a corona and an arc like we talked about before, and you can actually see the charge go back. So seeing is believing. And there it was. Okay, so charging by induction. It's also not a quantitative thing like rubbing. We aren't going to calculate the amount of charge that we pushed around.
Dielectrics are insulators. What is a dielectric? A dielectric is a non-conducting material and has no free electrons. The electrons in a dielectric are bound within the atoms. The examples are carbonate, glass, and mica. When an external electric field is applied, the electrons are not free to move anywhere, but they are realigned in a specific way. A dielectric is made up of either polar molecules or non-polar molecules. Now let us see what are non-polar molecules. A non-polar molecule is one in which centers of positive and negative charges coincide. As a result, it has no permanent dipole moment. What are the examples of non-polar molecules? They are hydrogen, oxygen, and carbon dioxide. When an external electric field is applied, the centers of positive and negative charges are separated by a small distance, which induces dipole moment in the direction of the external electric field. Then the dielectric is said to be polarized by an external electric field, and that is shown in figure 1.48. These are the non-polar molecules without external field and with the external field. Let us see what are polar molecules. In polar molecules, the centers of the positive and negative charges are separated even in the absence of an external electric field. They have a permanent dipole moment. Due to thermal motion, the direction of each dipole moment is oriented randomly, as in given in 1.49a. Since the net dipole moment is 0 in the absence of an external electric field, the examples of polar molecules are water molecule, N2O, HCl, and H3. When an external electric field is applied, the dipoles inside the material tend to align in the direction of the electric field. When an external electric field is applied, the dipoles inside the material tend to align in the direction of the electric field. Hence, a net dipole moment is induced in it. Then the dielectric is said to be polarized by an external electric field, as shown in this figure. Next, we will study about the polarization. What is polarization? In the presence of an external electric field, the dipole moment is induced in the dielectric material, and polarization P is defined as the total dipole moment per unit volume of the dielectric. For most dielectrics, which are linear isotropic in nature, the polarization is directly proportional to the strength of the external electric field, and that is written as P equal to Ze E external, where Ze is a constant called the electric susceptibility, which is a characteristic of each dielectric. Next, we are going to study about induced electric field inside the dielectric. When an external electric field is applied on a conductor, the charges are aligned in such a way that an internal electric field is created, which tends to cancel the external electric field. But in the case of a dielectric, which has no free electrons, the external electric field only realigns the charges so that an internal electric field is produced. The magnitude of the internal electric field is smaller than that of an external electric field. Therefore, the net electric field inside the dielectric is not zero, but is parallel to an external electric field with magnitude less than that of the external electric field. For example, let us consider a rectangular dielectric slab placed between two oppositely charged plates. That is a capacitor as shown in the figure 1.50, like this. There are two charged conductors which are having positive charges on one side and negative charges on the other side. So the uniform electric field between the plates acts as an external electric field, E external, which polarizes the dielectric phase between the plates, and the positive charges are induced on one side surface and negative charges are induced on the other side of the surface. But inside the dielectric, the net charge is zero even in a small volume. So the dielectric in the external field is equivalent to two oppositely charged sheets with the surface charge densities plus sigma and minus sigma b. These charges are called bound charges. They are not free to move like free electrons in conductors, and that is shown in this figure. And for example, the charged balloon after rubbing sticks onto a wall like this. The reason is that the negatively charged balloon is brought near the wall. It polarizes opposite charges on the surface of the wall, which attracts the balloon like this. So here the negative charges are there in the balloon, and it induces positive charges on this side. Therefore, the balloon sticks to the wall. And let us see what is meant by dielectric strength. When the external electric field applied to a dielectric is very large, it tears apart the atoms so that the bound charges become free charges. Then the dielectric starts to conduct electricity. This is called as dielectric breakdown. Now let us see what is dielectric strength. That's the maximum electric field the dielectric can withstand before it breaks down. That is called as dielectric strength. For example, the dielectric strength of air is 3 into 10 power 6 volt per meter. So that's about 30 lakhs volt per meter. If the applied electric field increases beyond this, a spark is produced in the air. The dielectric strengths of some of the dielectrics are given in this table: mica, Teflon, paper, air, and Pyrex gas.